Welcome everyone, and thanks for your interest in this presentation about modeling non-ideal binary solutions using SysCAD Gibbs Free Energy Minimizer and optimizing solution parameters. My name is Tonay Marin Alvarado. I'm a senior simulation engineer at SysCAD, and it is my pleasure to share with you our work at Xmentes Pyro Community Day. I will start with a brief introduction and context of this presentation's main topic. First, by describing the importance of using fully defined thermodynamic models for the simulation of a steelmaking with hydrogen process, and how this problem was approached and solved using SysCAD Gibbs Free Energy Minimizer and its PGM programming language, used as a general controller in unit models. Then I'm going to expand on the concept of using non-ideal thermodynamic solution models by showing an example of optimizing parameters for binary mixture. This time uses SysCAD, COMS, automation, and Python. Okay, the topic of this presentation arose during the simulation of a green steelmaking process. You most certainly have seen the increase and interest and efforts to reduce the use of carbon in our industry, and steelmaking is of course no exception. So we wanted to look at the theoretical and practical limitations of using hydrogen to produce steel. In this process, of course, the idea is to replace carbon by hydrogen in order to reduce iron oxides into iron. The main difference between carbon-based steelmaking and hydrogen steelmaking is the fact that in the latter case, there are gases as reactants and products, whereas in the case of carbon reduction, there is carbon present as a solid reactant and the product is a gas, carbon monoxide or carbon dioxide, at least when looking at the global reaction of the overall process. We explored in detail the theoretical and practical limitations of this process in a paper for Conference of Metallurgists 2023 in Toronto. I invite you to find out more about this work in the reference shown here. In that article, we focus on a SysCAD model for a hypothetical direct iron reduction with hydrogen, covering a wide range of implications. However, in today's presentation, I want to focus on the thermodynamic model that was used to simulate the shaft furnace in SysCAD and the importance of being able to incorporate a full thermodynamic description of the iron-hydrogen-oxygen system in the reaction unit operation. When looking at direct reduction of iron oxides at relatively low temperatures, say below 1200 degrees Kelvin, the Bauer-Glasner diagram shows the boundary lines where the reduction of the various oxides takes place as a function of the gas composition. More specifically, as a function of the fraction of water vapor over the hydrogen and water vapor content. The main issue here is that to produce metallic iron, for example, at 1000 degrees Kelvin, almost 70% by volume of the gas must be hydrogen. Of course, this means that not all of the hydrogen that enters the system will be consumed, and of course, a high circulation load of hydrogen is required to maintain the low oxygen potential to produce iron. It is then of critical importance that our reactor model can accurately predict the phase stability for this system, as the shaft reactor can be assumed to be composed of several zones where the reduction process happens gradually from top to bottom, and it is of course controlled by the residual amount of hydrogen in the gases generated throughout the process. The challenge to add a robust and predictive phase stability model to the shaft furnace was clear from the beginning. In this animation, we show the calculated diagram by first using only pure compounds such as iron, iron oxide, and Fe3O4 or magnetite, using just standard Gibbs energy equations that can be found in the literature. However, within this temperature range, it is well known that iron is present at both BCC and FCC phases, with BCC having a strong magnetic ordering effect that contributes to the Gibbs energy. These magnetic effects are also present in the magnetite compound. Therefore, it was necessary to add this formulation to SysCAD's pure compound thermodynamic data. This improvement is reflected in diagram number 2 in this animation. Still, that was not enough to reproduce the diagram. It was recognized that iron oxide was actually present in the form of a monoxide solid solution with 2 end members. We then include a binary model for this solution using the Redlich-Kistner model, which I'll describe in more detail in the following sections. As shown in step 3 in the animation, this improved the results for the iron oxide iron boundary line, but the 2 boundaries considering a magnetite still needed improvement. So finally, magnetite was converted into a spinel phase with 4 end members. We then manually adjusted the activity coefficients of the spinel phase to fixed values, that is, values that are independent of temperature, to best match the expected results as shown in step 4 of the animation. This final model was then used in the Gibbs Free Energy Minimisation reactor for the shaft furnace in the overall hydrogen steelmaking diagram that I showed before. So, more in detail, the question is, how can a non-ideal model be implemented in SysCAD and automatically adjust activity coefficients as the Gibbs energy minimization proceeds? So, first of all, the Gibbs Free Energy Solver already provides the functionality to define phases and adjust the activity coefficients for each end members, therefore incorporating excess mixing effects in the overall Gibbs energy of the system. This screenshot shows the access window or configuration window of a Gibbs Free Energy Minimization reactor for the iron oxide hydrogen system in SysCAD. And you can see that the monoxide phase is designated as phase number 1, and the activity coefficient highlighted in yellow are set by the RK binary solution model, whereas the spinel, or phase number 2 here, has fixed values for activity coefficients for each of the end members. We found also that it was not necessary to use solution models for iron BCC or iron FCC phases, as the possibility for oxygen solubility in the metallic phases was negligible at these temperatures, and no other impurities were considered in this model. To automatically calculate the activity coefficients of a solution model in a Gibbs Free Energy Minimizer reactor, we implemented a general controller using SysCAD PGM programming language, where the interaction parameters can be set directly. In this case, the binary RK model was implemented as a class object, which allows to reuse the class and model systems with various non-ideal solutions. In this screenshot, the monoxide phase is shown, and we here are using first and second order interaction parameters for this solution. The class implementation of the binary model allows for detailed information, in this case for the monoxide phase, for both the input and output streams, and all of that information is, of course, automatically calculated. Here, the calculated activity and activity coefficients at equilibrium are highlighted for each one of the end members of the monoxide solution. Of course, other important variables like excess heat of mixing are shown as partial molar properties or as specific values for the mixture. With that detailed information, it is possible to apply correction terms to the heat flow or to the Gibbs energy difference between the output and input streams. In this particular example, HDIF, highlighted in one of the red boxes here, refers to the calculated heat flow without any correction or before applying any correction. And in this case, it would have been a negative value of minus 2.2 kilowatts. However, after taking into account the corrections for excess heat of mixing, the enthalpy difference is actually positive or endothermic. This, of course, highlights the importance of using full thermodynamic description on a reactor model, and not only for being able to achieve accurate phase stability, but also for better and more accurate energy balance calculations. In this last section, I want to show the next step in developing a full thermodynamic model, which is the possibility to optimize the thermodynamic parameters. In order to do that, new interaction parameters for let's say a non-ideal model can be obtained by a multivariable optimization system. In this case, we're using SysCAD Gibbs Free Energy Minimisation reactor with the binary RK model, which starts at some initial guess. We use 3 datasets corresponding to activity coefficients for each of the 2 end members of the monoxide solution, plus the XX Gibbs energy of mixing as targets to be optimized. Then, using Python and also using SysCAD GFEM automation library, a series of scenarios can be run to evaluate the target variables, that is, activity coefficients and Gibbs excess mixing energy, for each of the points in the dataset. At each iteration, then a global error function can be calculated. Then the optimizer function from a SciPy, for example, one library available for Python, will adjust the SysCAD tags corresponding to the first and second order solution parameters, trying to minimize the global error. In this animation, the progress of the optimization routine is observed. Starting from an initial guess, the optimizer starts by finding a symmetrical solution, and then, after a few more iterations, is able to adjust the second order parameter to reproduce the non-symmetrical nature of the model, rapidly converging to the final parameters. In this example, 3 different error formulas definitions were plotted. However, just one of them, which is the sum of the relative errors squared, the blue line in the bottom graph, is used for optimization. The optimized parameters for the monoxide RK model were then used in the green hydrogen model discussed in the previous section. Finally, to summarize, using the thermodynamic description of a system, including a non-ideal solution, can be of critical importance for accurate predictive process model. In the case of steelmaking with hydrogen, we see that the correct excess concentration of hydrogen in the gas phase can only be predicted by a full non-ideal model. As well, accurate energy balance, considering excess heat of mixing, can prevent serious errors in heat balance calculation. So, which show in this example, changing from exothermic to endothermic by considering the excess terms for excess Gibbs, heat of mixing. Also, SysCAD will soon allow magnetic ordering contributions terms for compound energy equations. It will allow for the definition of non-ideal Gibbs energy by defining phases and adjusting activity coefficients. RK binary solution models using PGM controllers provide more predictive capabilities and allow better energy balance calculation. And finally, together with Python, SysCAD can fully optimize and generate thermodynamic parameters for non-ideal solutions. Next steps would be for, as I mentioned before, finalizing magnetic order and contribution terms for compounds Gibbs energy equation. Then to provide native binary interactions in Gibbs free energy reactors. That means no need for to write a specific general controller using the PGM language. Better convergence with a Gibbs Free Energy Minimizer solver is going to be available. Of course, higher order extrapolation is important to continue being able to provide robust and complex thermodynamic calculations. That means extrapolation from binary to ternary systems or quaternary system, provide for ternary interaction parameters, etc. And of course, after this, the following steps would be to provide implementation for other solution models, not just RK, but very common models such as sublattice model, extended quasi-chemical model, etc. Could be implemented in the future. Thank you very much for your attention. I hope you find this presentation interesting, and if you wish for more information, please do not hesitate to contact us by email or through our website. Thank you very much.